In this presentation, we are gonna present an under-developing project called AI Sprint, Advancing Design and Runtime Management of AI Applications. And this presentation aims at highlight the main challenges and design principles behind it. As an overview of this presentation, we first express an introduction and motivation of the project, and then state the objectives and a running example. We also explain AI Sprint architecture and its design time and runtime approach, and finally we have a conclusion. The importance and pervasiveness of artificial intelligence and deep learning are increasing dramatically in these years. Nowadays, the accelerated migration towards mobile computing and Internet of Things is determining an evaluation of AI and big data applications. So having computing resources at the periphery of the network can benefit from reduced latency, lower bandwidth requirements, and increased energy efficiency and privacy protection. According to this trend, edge intelligence is expected to become the foundation of many AI application use cases, spanning from predictive maintenance to machine vision and healthcare. In this presentation, we introduce AI Sprint project, which will make it possible to seamlessly design and partition AI applications among the current plethora of cloud-based solutions and AI-based sensor devices. This project aims at achieving the following objectives. Provide design and development tools for the implementation of AI applications consuming resources across the computing continuum, including multi-clouds, edge servers, and AI-enabled sensors. The design environment will include programming abstractions to hide the communications across components and also quality annotations to express performance, accuracy, privacy, and security constraints. The second objective of the project is also providing tools for secure execution and the privacy preservation of applications. This aims to ensure confidentiality and integrity of application data across the computing continuum, secure application configuration and execution, and data transfers, provide privacy preserving solutions through AI model partitioning and edge training and retraining. The third objective is developing a runtime environment for application execution and monitoring that implements policy orchestrating the application's execution across the computing continuum via application deployment to accelerate the delivery of applications and AI models, monitoring of edge-to-cloud resources, dynamic energy aware and optimal resource allocations to fit workload requirement, and resilient applications execution with performance guarantees. Finally, the last objective is providing advanced solutions for AI architecture enhancement and deployment by assimilating newly generated data from the field, integrating new AI sensors, and adding new privacy, security, and application performance constraints. In order to provide the intuition of the AI Sprint solutions benefit, we introduced an application inspired by one of the AI Sprint use cases, a wind farm, as shown in the figure. In this application, we have a complex machine learning pipeline that involves several components. The first component, C1, is in charge of taking a picture from the airborne drone controlled remotely by a human operator. The second component C2 is a classifier which checks if the image quality is sufficient for further processing, and otherwise it triggers the acquisition of a new picture. Component C3 is a complex computer vision based application which monitors the inspection campaign and guarantees that this cover the complete site. Component C4 provide an initial feedback to the operator and notify if the inspected part like a blade has a problem. Component C5 identify the specific problem like a crack. And finally, component C6 is a large-scale analytic application which identifies patterns in part degradation by considering external factor and historical data. This picture represents the general architecture of AI Sprint. AI Sprint architecture includes two main parts. The first part is design time tools, and the second one is runtime tools. AI Sprint design time solutions include the tools for annotating AI applications with non-functional quality of service constraints and guide code parallelization, evaluating priori performance of AI applications, and we can provide a solution which guarantees the performance both at training and at inference time, identifying and automating the search for the most accurate deep neural network, and finally exploring multiple candidate deployment for the application component, maximizing resource efficiency and minimizing the cloud usage costs. In order to run applications transparently on a heterogeneous architecture, we need a runtime environment. The AI Sprint runtime environment will include tools to support the continuous deployment of AI applications, support application components, concurrent execution, reacting to node failures, and identifying their optimal placement, and resource capacity for guaranteed performance, trigger automated model retraining, leveraging on solutions for training and retraining at the edge, and optimize the scheduling and assignment of accelerator device among competing training jobs. Now we investigate AI Sprint design time tool in wind farm use case. In design and programming abstractions, application components annotations to specify intra and inter components parallelism. For example, C3 is a complex application, and internal parallelism can be exploited to improve application execution time and to reduce the edge server required capacity. The base of the AI Sprint programming layer will be the PyCom's programming framework that aims to facilitate the parallelization of existing Python application, which is mainly responsible for identifying the functions to be executed as asynchronous parallel tasks and annotating them with standard Python decorators. Design and programming abstraction also allow us to specify constraints on application performance, security, privacy, and underlying resources. For example, component C2 can be automatically allocated by the design tools on the drone or on the edge server according to the application performance constraints. For example, image processing time should be less than 30 milliseconds. On the other hand, to enforce a high security level for execution of C6, another annotation will force C6 code to run in a secure enclave. AI Sprint will provide also a performance modeling approach based on machine learning to predict the execution time of inference or training tasks of AI models. We develop solutions for architecture search, which means that from labeled dataset state-of-the-art provide solution with a higher accuracy, but actually since we introduce performance model, we will trade off and introduce constraints on performance, which means execution time guarantee. For example, you can see here in component C5 we have another quality annotation which express a constraint on accuracy and another constraint on the inference. Finally, AI Sprint will develop solutions for breaking down large deep networks for privacy preserving analytics. For example, since component C4 is annotated with privacy protection, the AI model will be split into two components, which is shown by yellow element in the figure. AI models will develop also solution for a design space exploration, so the goal will be subject to an additional step of design space exploration where multiple alternative candidate deployments will be evaluated to find the optimal component placement, maximizing resource efficiency while minimizing the cloud usage cost given the quality of service constraints. For example, as you can see here with quality annotation, here we say that candidate for C6 deployment are P1 large VM and P2 medium VM, and the tool will automatically find the best solution. For the runtime environment, AI Sprint will include tools to 4 goals. As a continuous deployment, AI Sprint provides a cloud edge orchestrator, enabling the automatic deployment of AI application models and components without manual provisioning by starting from Tosca recipes. As a programming framework runtime, AI Sprint will provide a runtime system in charge of supporting concurrent code execution, automatically detecting and enforcing the data dependencies among components, and execute tasks in parallel by leveraging pipelines. Within AI Sprint, pipelines runtime will be extended to support the serverless computing paradigm. For example, given the edge server current load, a component can be dynamically allocated and run as a function on the edge server or in the cloud, reducing operation costs and still providing execution time guarantees for the overall application. Application components migration will leverage Cracker. In order to privacy preserve, AI Sprint will provide a general purpose framework towards continuous integration of AI model updates and perform training offline without any system support for continual model updating. Edge training and retraining in AI Sprint will leverage federated learning algorithms. For example, during the training, component C3 submodel forward pass will be processed on an edge server, which will send to the cloud only preprocessed data. The cloud in turn will compute the loss function and compute C4 parameters gradients without accessing the raw images. As a conclusion, the core benefits of AI screen tools are as follows: reduction of skill shortage and steep learning curves in the development of AI software, shorter time to market for AI applications that meet performance, security, and privacy requirements, reduction of costs for software developers to design and evolve AI applications running at the edge, and reduction of costs to operate AI applications and increase value for cloud provider and edge users. Thanks for your attention.